Web crawler multi-threaded in Python, and in part 1 we discussed why you need to use a Threads API. You cannot use async IO. In this video we're going to compare and contrast different Threads APIs and pick the right one for this problem in Python. So Python has more than 5 native ways to work with threads, but we'll be able to cover them in under 5 minutes, but it's going to take more than 1 minute because there's so many ways to work with it. All right, so technically you can use the async IO module with the 2-thread method. The problem is that there's no reason to do this, so the whole async IO abstraction is extraneous in the web crawler problem. The only reason you would really want to import it is if you're just super comfortable with async IO already, and then the interviewer is going to ask you, why did you choose this instead of a thread native module? And you're going to say, just because I'm really comfortable with the code, which is fine, but it's really not the best answer. The best answer is you want to understand the fundamental trade-off between threads and coroutines. So async IO, we implement it because it contains a different abstraction, which is a promise-like structure, and it's called a coroutine. And the overhead of a coroutine relative to a thread is like 100 times less. So the lower memory usage allows us to get more network traffic throughput. So if you're IO bound and you want to take a bunch of requests, this is why it's used in Fast API. If you want to have a bunch of input and outbound requests, it's super useful because the memory overhead is low. But the problem is it doesn't magically unblock the loop. It doesn't unblock the event loop. So it doesn't actually achieve true parallelism, which is the thing we really care about in the web crawler problem. You might think web crawler is about network chatter, but it's not. It's about inheriting a legacy synchronous function and moving that off the event loop, and you need threads to do that. So the latter 4 modules all achieve true parallelism. They can solve the problem, but it may or may not be optimal, and it may or may not be good for your syntax, your completion in an interview setting, and your discussion with the interviewer. And that's the real pitfall on number 2. So Q.Q, this is not the only Python native module called Q, and it's not even the only Q that you can use for concurrency and parallelism. There are other ones too, which makes things really confusing for your own memory and for when you're talking to your interviewer. Your interviewer might not even be familiar with Python, so they might be thinking of a Q in a totally different language, and that can be, which may not have native multi-threading support, and so that can be really confusing. So I recommend you just avoid the Q entirely. Now, if you're already really experienced with the Q, it can solve this problem optimally, and it's actually really flexible, and you can use it in other concurrency problems too. So it's a really nice structure if you know what you're doing, but be expected for, the interviewer is going to ask clarifying questions. You need to be able to answer them well, and you need to know the syntax for this module, which it's not the most concise syntax, but if you know it well, it's going to work. Executor.submit with a DEC will not give you an optimal solution. That's the reason to avoid this. So submit does not return results in the order of completion. So you're going to submit a list of asynchronous tasks to the executor. That's going to send it over a number of threads. And the order they come back is going to be the original order of the sent list. So if I have tasks A, B, C, if C completes first, with a DEC approach or with a list approach or with an iterative approach, if I'm waiting for that first task, I'm going to have to wait. Even though C completed first, I'm going to have to wait for A to go down the list. That's why this approach is not optimal. That's the nature of the submit return order, is that it's going to return according to the submission order, not according to the completion order. Map, on the other hand, does return in completion order. So map has the cleanest syntax. It's super, super awesome if you know a static list of tasks to be done. And so the problem is that the web crawler problem is not such a case. The web crawler problem, the system can crawl a page, and then that page might chain. It might say, hey, we crawled page A, and page A contains a link to page B. And so now you need to actually dynamically grow your search frontier. And you need to basically chain these asynchronous operations. It's not a static list of async tasks. So that's why we don't want to use for in this problem, but in other kinds of concurrency problems in Python, that is a super clean solution, and the syntax is really nice. It's basically like doing a for loop. It's that easy. But what we want for the web crawler problem is we want executor.submit with as completed. So this is going to allow us to dynamically grow the frontier, meaning that chaining, like page A says that, hey, you should continue to crawl page B and so on. It'll support that. And it has a relatively concise syntax. Okay, so here's the actual syntax. We get a thread executor pool. You're going to import futures. And here's my workers. And this is the key data structure. It's a dictionary of future objects to the start URL. And I'm going to treat that kind of like a queue. I'm going to iterate over it and pop out, even though it's a dictionary. This is the thing that's interesting about this pattern, and it's actually super elegant. So I'm going to pop out dictionary records, and that will eventually clean itself up and terminate the while loop and will be done. But this way, I can append to that dictionary and grow the frontier dynamically. So you see, I'm going to go through these futures in completion order as completed. That means I'm getting that pretty much as true parallelism as you can get with Python anyway. So you still have the single thread, but it's highly concurrent, and you'll pop out a record in completion order, and you'll say, okay, here's the retrieved results, add them to the list of seen URLs that you've crawled. And if it's a new one, then you can chain this way. Hope this made sense. Follow for more Python stuff and LeetCode. Drop a comment if there's a particular LeetCode question you're interested in, by the way.